Hi, and welcome to the videos for section 5.4 for Math 181. This is the first of two videos for this section. Section 5.4 is a pretty important one in terms of this calculus class, because section 5.4 is the fundamental theorem of calculus. So if you're going on to other calculus classes, if you're going on to other math classes even, this is going to be referenced a lot, the fundamental theorem of calculus. And so you'll sometimes see it abbreviated FTC, fundamental theorem of calculus. And what fundamental theorem of calculus does is it establishes a connection between our differential calculus, the stuff we are doing maybe the first 2/3 of the semester, with the integral calculus, which is what we've done here the last chapter really, chapter 5. So again, the derivations, the proofs, these are on pages 291 through 294. So again, you know by now, I don't spend the video time on this, and you can see why. 3 pages of derivation and proof. So it doesn't make sense for me to, spend 20 minutes of time on video showing you the derivation and proof when you can go to the book, kind of follow through if you really want to know it. But ultimately, you're going to get to the fundamental theorem of calculus, part 1. So there's 2 parts to it. And you might see this abbreviated as FTC1. And it says the following: if f is continuous on the closed interval AB, then the function g defined by g of x is the integral from some value a to x of the function f of t dt Let me double check this real quick, make sure I got the notation written down right. Yeah, okay. So a to x, and then x is less than or equal to, is greater than a or less than or equal to some value b. So the function g defined by this is an antiderivative of f. So that is to say, g prime of x is equal to f of x for x is between some value a and b. So this is, again, kind of going back to our derivatives, stuff we were doing early in the semester, is that our derivative evaluated at some value x is the same as the function if we take the antiderivative or the integral of some function f of t. So let's see what it looks like in an example format. And it's basically the stuff that we've been doing all along. It just helps us, without having to do a lot of work, we can reference this fundamental theorem of calculus to give us answers. So for example, find the derivative of g of x, which is equal to 0 to x square root of 1 plus t squared dt. So, if we look at fundamental theorem of calculus, first of all, is f continuous? So this right here, this is what? This is our f of t. Well, it's a square root function. It is continuous from 0 to whatever. If this is 10, it's still continuous. If it's 100, it's still continuous. So given that g of x is equal to this format, 0 to x f of t dt, we're trying to find the derivative of g prime, of g of x, right, to give us g prime. So by the fundamental theorem of calculus, part 1, g prime of x, and because this guy is continuous, we can just say that this is equal to f of x. So f of t is this, so f of x would be if we plug in x for any value of t, so that's just what? That's just the square root of 1 plus x squared. So we don't actually need to figure out what's this integral, then take the derivative. The fundamental theorem of calculus already says that if f is continuous, then whatever this integral piece is, the derivative of this function, g prime, is just this f function when we plug in our value x. So again, it saves us a lot of time. So I guess the main thing is, like, if you have this on an exam or if you have it on a homework and you're told to find the derivative and it's given to you in this form, the big thing is, okay, is f of t continuous? As long as it is, then you can state that by the fundamental theorem of calculus part 1, g prime is just this piece when we plug in x. So that's our fundamental theorem of calculus part 1. Part 2 is what we did actually in section 5.4, which is the evaluation theorem. So we now add it to what's known as the overall fundamental theorem of calculus. So we have the following. Suppose f is continuous on the interval, closed interval, AB. Then we have the two different parts that we can use to our advantage. The first one was part 1, which we just had. That is, if g of x is the integral from a to x, f of t dt, then g prime of x is just f of x. And that's this example that we saw right here, part 1. And so you can state it as, realistically, you could say by the fundamental theorem of calculus, or if you want to get specific, by fundamental theorem of calculus part 1. Why are you saying that g prime is just this guy? Part 2, which again was the evaluation theorem that we saw in the last video, the last section, 5.4. And that says that the integral from a to b of fx dx is equal to just f of b minus f of a, where capital F is any antiderivative of little f, so i.e. capital F inverse is equal to our little f. So again, evaluation theorem, fundamental theorem of calculus part 1, we include it into the entire fundamental theorem of calculus. So that's it. We've done a bunch of these type of examples. These examples are just going to be the same thing, not really a lot of work to show. The biggest thing we have to do is say that, okay, is f of t continuous? And as long as it is, then we can make this jump. If it's not, then obviously we can't use the fundamental theorem of calculus. So that's the end of the first video for section 5.5. Excuse me. Come on back, we'll look at the mean value theorem, and that'll wrap up section 5.5.